In September of 2023, the James Webb Space Telescope found carbon on the surface of Jupiter's moon Europa. Not carbon from a meteorite, not carbon deposited by solar wind, carbon that had come up from inside. From the ocean beneath the ice, two separate teams published their findings on the same day in Science, and both papers said the same thing. The carbon dioxide was concentrated in a region called Terra Regio, a zone of fractured, chaotic terrain where the ice shell has been broken apart and reassembled, where material from the ocean below is believed to well up to the surface. The carbon was internal. It came from the water, and you probably never heard about it. You heard about the Webb telescope finding the oldest galaxies. You heard about it detecting atmospheres on exoplanets. But the discovery that a moon in our own solar system, a moon with an ocean holding 2 to 3 times the volume of all of Earth's oceans combined, has confirmed carbon cycling from its interior to its surface, a discovery that checks one of the final boxes on the short list of requirements for life as we understand it, that did not lead the news. It did not trend. It settled quietly into the archive of published papers and moved on. That is strange. And it gets stranger when you realize what else has been confirmed about Europa in the last few years, because the carbon was not the first surprise. It was the last piece in a pattern that had been building for over a decade, a pattern that a growing number of physicists and chemists are now willing to describe using a word that most scientists avoid. That word is inevitable, not possible, not plausible, not worth investigating, inevitable. As in, given what we now know about Europa's ocean, given what we now know about the physics of far from equilibrium systems, given what at least 7 independent theoretical frameworks published in the last 10 years are converging on, the emergence of complex, self-organizing chemistry in that ocean is not a question of luck. It is a question of law. And there is a reason that framing makes people uncomfortable. There is a reason most press releases about Europa still use words like habitable and potentially and conditions consistent with. Because if the strong version of this claim is true, if the physics really does compel what these researchers say it compels, then the implications do not stop at Europa. They come back here. They reach into the story you were told about your own existence. The story where life on Earth was a miracle, a 1 in a billion chemical accident, fragile and precious and unrepeatable. That story does not survive what we are about to go through. And the people who understand the data best are the ones least willing to say that out loud. There is a word for what happens when you give a thermodynamic system this much energy and this much time and this many raw materials. Physicists have a word for it, and it is not maybe. So here is what we're going to do. We're going to start with the ocean, not the theory, not the philosophy, the ocean itself, what it actually is. Because the single biggest misconception about Europa is that it is a frozen moon with some slush underneath, a ball of ice with maybe a thin layer of cold water at the bottom. That is not what Europa is. What Europa actually is, once you look at the data that has accumulated since the Galileo spacecraft first confirmed the ocean's existence in the year 2000, is something that should have rewritten the textbooks a long time ago. Europa is slightly smaller than Earth's moon. Its diameter is 3,122 kilometers, roughly 90% the size of our moon. It orbits Jupiter at a distance of about 671,000 kilometers, deep inside Jupiter's magnetosphere, completing one orbit every 3.5 Earth days. It is tidally locked, meaning the same face always points toward Jupiter, and it is caught in a gravitational resonance with two other moons, Io and Ganymede, called the Laplace resonance. For every single orbit Ganymede completes, Europa completes exactly 2, and Io completes exactly 4. This resonance is not a curiosity. It is the engine that makes everything else possible, because it prevents Europa's orbit from circularizing. The orbit stays slightly elliptical, which means Jupiter's gravitational pull on Europa varies continuously, flexing the moon's interior, generating heat through friction. Tidal heating, that is what keeps the ocean liquid, not the sun. The sun is 5 times farther away than it is from Earth, and sunlight at Jupiter is 25 times weaker than what you feel on your skin right now. Europa's ocean exists not because of the sun, but because of gravity. Because Jupiter will not let it freeze. The ocean was confirmed on August 25, 2000, in a paper published in Science by Margaret Kivelson and her team at UCLA. Kivelson was the principal investigator for the magnetometer on NASA's Galileo spacecraft, which had been orbiting Jupiter since 1995. What the magnetometer found during a flyby on January 3, 2000, was that Europa's magnetic field was not static. It was changing. It was responding to Jupiter's rotating magnetic field in exactly the way you would expect if there were a layer of electrically conductive fluid beneath the ice. The only natural material that could produce the observed signal at the depths and conductivities required was salt water, not fresh water, not ice. Salt water with a conductivity greater than 0.06 Siemens per meter at a depth of less than 200 kilometers beneath the surface. Think about that for a moment. This was 25 years ago, a quarter of a century, and the confirmed existence of a saltwater ocean twice the volume of all the water on Earth, on a moon orbiting the largest planet in our solar system, has still not fully registered in the public imagination. People still talk about Europa the way they talk about Mars, as a place that might have had water once, a long time ago. Europa does not might have had anything. Europa has an ocean right now. It has had that ocean for over 4 billion years. It is older than multicellular life on Earth. The volume alone is staggering. Estimates place Europa's ocean at roughly 3 billion cubic kilometers of liquid water. Earth's oceans hold about 1.3 billion cubic kilometers. So Europa, a moon you could fit inside the continental United States, contains somewhere between 2 and 3 times more liquid water than the entire planet you are sitting on. That water sits beneath an ice shell that, according to the most recent measurement from the Juno spacecraft's microwave radiometer, published in Nature Astronomy in December of 2025, is approximately 29 kilometers thick, plus or minus 10. That measurement came from Juno's close flyby on September 29, 2022, when the spacecraft passed within 352 kilometers of Europa's surface and aimed 6 microwave frequencies into the ice. 29 kilometers of ice sounds impenetrable. And it is to us. But the ice shell is not a static barrier. It is a geological system in its own right, and it is doing something that fundamentally changes how you should think about Europa's ocean. In 22T, a team led by Riley Kullberg and Dustin Schroeder at Stanford published a finding in Nature Communications that had not been anticipated by any Europa model. They were studying Europa's surface features, specifically the double ridges that crisscrossed the moon's surface, parallel raised lines running for hundreds of kilometers. Double ridges are the single most common landform on Europa. They are everywhere, and nobody had a convincing explanation for how they formed. Kullberg's team found the answer not on Europa, but in Greenland. Using NASA IceBridge, ice-penetrating radar data, they discovered a double ridge in northwest Greenland with the exact same geometry as Europa's ridges, scaled for the difference in gravity. The Greenland ridge had formed over a shallow pocket of liquid water that had repeatedly frozen, expanded, fractured the ice above it, and refrozen. If the same process operates on Europa, and the geometric match is precise enough that it almost certainly does, then shallow liquid water is not rare on Europa. It is everywhere. The double ridges are not scars, they are signatures. Every one of them marks a place where water exists or recently existed within a few kilometers of the surface. This connected to an earlier finding by Brittany Schmidt, then at the University of Texas, published in Nature in November 2011. Schmidt proposed that Europa's chaotic terrain, those jumbled, disrupted regions like Terra Regio, where the JWST found the carbon, form above shallow water lenses perched just 3 or so kilometers down inside the ice shell. Her model resolved a debate that had lasted over a decade about whether Europa's ice shell was thin, a few kilometers, or thick, 20+ kilometers. The answer turned out to be both. The shell is thick overall, but it contains pockets and lenses of liquid water at shallow depths, and those pockets are the sites of active geological exchange between the ocean and the surface. This matters enormously because of what is happening on the surface. Jupiter's magnetosphere is one of the most punishing radiation environments in the solar system. It is roughly 20,000 times stronger than Earth's magnetic field and generates a radiation belt about 20,000 times more intense than Earth's Van Allen belts. Europa's surface receives approximately 540 rem of radiation per day. To put that in perspective, the total lethal dose for a human is around 5 sievert, which is 500 rem. Europa's surface gets a lethal human dose every single day. You would not last 24 hours standing on the ice, but that radiation is not just destructive. It is doing chemistry. When high-energy electrons and ions from Jupiter's magnetosphere slam into Europa's ice surface, they break apart water molecules. The hydrogen, being light, escapes to space. What stays behind are oxidants. Hydrogen peroxide, molecular oxygen. When the radiation hits sulfur that has been deposited on the surface from Io's volcanic eruptions, it produces sulfuric acid and sulfur dioxide. Europa's surface is a radiation-driven chemistry lab, and Jupiter is the power source. The moon is being continuously bathed in enough energy to synthesize reactive chemicals that on Earth are associated with biological metabolism. Now here is where the picture starts to get uncomfortable, because those oxidants do not just sit on the surface. The ice shell moves, it convects. In some models, warm ice rises from below, cold ice sinks from above, and material gets cycled. The chaotic terrain, the double ridges, the shallow water lenses, all of these are mechanisms by which surface material can be transported downward, through the ice and into the ocean. A 2010 study by Kevin Hand and others estimated that oxidant delivery to the ocean could range from about 100,000 moles of molecular oxygen per year at the low end to as high as 300 billion moles per year at the high end. The high-end estimate, published by Richard Greenberg, calculated that the oxidant flux could support roughly 3 million tons of macrofauna. That is not a typo. 3 million tons. Greenberg was not a fringe figure. He was a professor at the University of Arizona's Lunar and Planetary Laboratory, and his calculations were published in peer-reviewed journals. In 2024, the oxidant picture shifted. Juno's JADE instrument, during the same September 2022 flyby that measured the ice thickness, detected Europa's oxygen production rate directly by measuring the charged particle environment. The result, published by Saleh and colleagues in Nature Astronomy, put oxygen production at roughly 12 kilograms per second, about 1,000 tons per day. Previous estimates had ranged from 5 to 1,100 kilograms per second, so the Juno measurement lands at the low end. This matters for the energy budget. Fewer oxidants reaching the ocean means less chemical energy available. But even at 12 kilograms per second, the oxidant flux is not zero. It is 1,000 tons a day, every day, for billions of years. And oxidants are only half of the equation, because the ocean is not just being fed from above, it is being fed from below. Europa's ocean sits on a rocky seafloor. That rock is in contact with water, and when water interacts with iron and magnesium-rich rock at the temperatures and pressures found at Europa's seafloor, something specific happens, a reaction called serpentinization. Water reacts with minerals like olivine, producing serpentine, magnetite, brucite, and molecular hydrogen gas, a fuel. The iron in the olivine gives up electrons to the water, and the water gives up its oxygen. The products are new minerals and free hydrogen. On Earth, serpentinization occurs at mid-ocean ridges and in ultramafic rock formations, and it powers entire ecosystems that never see sunlight. The Lost City hydrothermal field in the mid-Atlantic, discovered in the year 2000, runs entirely on serpentinization. Water temperature at Lost City ranges from 40 to 90 degrees Celsius. The fluids are highly alkaline with a pH around 9 to 11, and the system is saturated with hydrogen. Microbes there live on the energy gradient between the hydrogen-rich vent fluid and the oxygen-bearing seawater. They do not need light. They do not need a surface. They need a chemical gradient. On Europa, the conditions for serpentinization are not only present, but potentially more extensive than on Earth. A 2016 study by Steve Vance, Kevin Hand, and Robert Pappalardo at JPL, published in Geophysical Research Letters, modeled the water-rock interaction and found something remarkable. On Earth, water can penetrate about 5 to 6 kilometers into the crust through fractures before temperature and pressure seal the cracks. On Europa, because of the lower gravity, fractures can extend to roughly 25 kilometers into the rocky interior. That is 4 to 5 times deeper than Earth. The volume of rock available for serpentinization on Europa is dramatically larger relative to the ocean volume than on Earth. Vance's team calculated the hydrogen production rate from serpentinization at between 1 billion and 50 billion moles per year. For comparison, Earth's total serpentinization-driven hydrogen production is estimated at around 50 billion moles per year. Europa's lower gravity and deeper fracture networks give it a hydrogen budget in the same order of magnitude as Earth's. despite being a moon barely 90% the size of our own. Kevin Hand described the resulting setup as a battery. Oxidants from the irradiated ice surface are the positive terminal. Reductants from the serpentinizing seafloor are the negative terminal. The ocean sits in between. And the question, Hand said, is whether life and biological processes complete the circuit. But here is what Vance's paper actually showed, that most summaries leave out. The ratio of oxidant production to reductant production on Europa is comparable to the same ratio on Earth. On both worlds, oxygen production runs roughly 10 times higher than hydrogen production. The chemical imbalance is similar. The energy gradient is similar. Not identical, but in the same ballpark, within the same order of magnitude. Europa's ocean is not just habitable in the abstract. Its chemical energy budget structurally resembles the budget that supports life on the only planet where we know life exists. That finding was published in 2016. It should have changed the conversation. It did not change the conversation nearly enough. Because what it means, combined with the JWST carbon detection in 2003 and the sodium chloride detection in 2019, is that Europa's ocean has liquid water, dissolved salts, chemically similar to Earth's ocean, a confirmed internal carbon source, a continuous supply of oxidants from above, and a continuous supply of reductants from below, all sustained by tidal heating for over 4 billion years. Every individual item on the checklist for habitability has now been checked, not hypothesized, checked. And that is where most science communication stops. Habitable. Conditions consistent with life. Worth investigating. The framing is always cautious, always qualified, always leaving room for the possibility that Europa's ocean is just a very interesting puddle that never produced anything more complex than dissolved salt. The language of probability, the language of maybe. But there is a problem with that framing, and the problem is that it contradicts what an increasingly large body of physics is now saying, because the question is no longer whether Europa's ocean could support life. The question, according to at least 7 independent research programs published in the last 12 years, is whether the physics of far from equilibrium thermodynamics permits a system like Europa's ocean to not produce complex chemistry. And the answer, coming back from those programs, is unsettling, because several of them say no, that the chemistry is not optional, that it is compelled. To understand why, you have to leave Europa for a moment and go somewhere more abstract. You have to go to the place where physics and biology have been trying to shake hands for 50 years and keep missing. The standard story of the origin of life goes something like this. 4 billion years ago, Earth was a violent, hot, chemically rich world. Somehow, in that chaos, simple molecules combined into more complex molecules, which eventually formed self-replicating structures, which eventually became cells, which eventually became everything alive today. The word somehow in that sentence is doing more work than any word in the history of science, because nobody knows how it happened, not in detail, not with the kind of specificity that would let you write down a chemical equation and say, this is the reaction that started it. The most popular framework for decades was the RNA world hypothesis. The idea, named by Walter Gilbert in 1986, but building on earlier work by Alexander Rich and by Francis Crick and Leslie Orgel, is that RNA came first. RNA can store genetic information like DNA and can catalyze chemical reactions like a protein. So maybe Before DNA and proteins existed, RNA served both functions. Thomas Keck and Sidney Altman won the Nobel Prize in 1989 for discovering ribozymes, catalytic RNA molecules, and the ribosome itself, the machine that builds all proteins in all living cells, turns out to be fundamentally an RNA machine. The evidence for an RNA world is real, but the problems with the RNA world are also real, and they are severe enough that Harold Bernhardt, in a 2012 review in Biology Direct, titled his paper, "The RNA World Hypothesis, the worst theory of the early evolution of life, except for all the others." RNA is chemically complex. Building it from scratch requires 4 specific heterocyclic bases arranged on a sugar phosphate backbone with precise 3', 5' linkages. RNA is inherently unstable and breaks down readily at higher temperatures. No one has ever achieved genuine self-replicating RNA in the laboratory despite decades of effort. And most critically for Europa, many RNA world scenarios depend on ultraviolet light from the sun driving prebiotic chemistry on a planetary surface. Europa has no surface chemistry driven by UV light. Its surface is irradiated by Jupiter's magnetosphere, not the sun, and its ocean is sealed beneath kilometers of ice in permanent darkness. If life emerged on Europa, it did not follow the RNA world playbook. Something else would have had to happen. Something that does not require sunlight, does not require a surface, and does not require the spontaneous assembly of one of the most fragile and complex molecules in biochemistry. And this is where a biochemist at University College London enters the story. Because Nick Lane has spent his career arguing that the RNA world has it backwards, that life did not start with replicating molecules at all, that it started with energy. Lane, building on the pioneering work of Michael Russell at NASA's Jet Propulsion Laboratory, developed the most detailed hypothesis connecting hydrothermal vents to the origin of life. The argument goes like this. In Earth's earliest ocean, over 4 billion years ago, alkaline hydrothermal fluids seeped up from the seafloor. These fluids were hot, around 70 degrees Celsius, highly alkaline at pH 9 to 11, and saturated with dissolved hydrogen from serpentinization. They entered an ocean that was mildly acidic, around pH 5 to 7, rich in dissolved carbon dioxide, and much colder. Where the vent fluids met the ocean water, thin walls of porous mineral formed, iron-nickel sulfide minerals. And across those thin mineral walls, a pH gradient of 3 to 6 units persisted continuously, driven by the chemistry on either side. Here is the key. That pH gradient, roughly 200 millivolts across a thin inorganic membrane, is the same magnitude and the same polarity as the proton motive force that every living cell on Earth uses to generate energy. Every cell, bacteria, archaea, your own mitochondria, they all push protons across a membrane to create a voltage, then use that voltage to drive the synthesis of ATP, the universal energy currency of life. Lane's argument is that cells did not invent this gradient. They inherited it. The vents were already doing it. The very first proto-life did not need to evolve an energy source because the energy source was already there, built into the geology, running for free. The thin mineral walls at the vents contained iron-sulfur clusters, structurally similar to the cofactors in modern metabolic enzymes like ferredoxins, some of the most ancient proteins known. The continuous supply of hydrogen from the vents and carbon dioxide from the ocean mirrors the substrates of the acetyl-CoA pathway, also called the Wood-Lungdahl pathway, which is the only carbon fixation pathway found in both major domains of microbial life, bacteria and archaea. If a metabolic pathway is shared by both domains, it almost certainly predates the split between them, meaning it is among the oldest biochemistry on Earth, and it runs on exactly the chemicals that alkaline hydrothermal vents provide. In 2019, Sean Jordan and colleagues at UCL, working in Lane's group, demonstrated in the lab that protocells, simple fatty acid vesicles, can form and remain stable in hot alkaline seawater. This overturned a long-standing objection that fatty acid membranes would fall apart at high pH and temperature. The protocells not only formed, but maintained structural integrity in conditions mimicking alkaline vents. Lane's response was characteristically direct. He pointed out that icy moons of Jupiter and Saturn might also have alkaline hydrothermal vents in their seas, and that studies like his could help decide where to look for life beyond Earth. Michael Russell's research at JPL was funded by the NASA Astrobiology Institute's Icy Worlds team, specifically to investigate whether the alkaline vent scenario could work on Europa and Enceladus. The funding was not accidental. NASA was already thinking about this. Now check Europa against the alkaline vent checklist: liquid water, ocean in contact with a rocky seafloor, confirmed. Serpentinization, producing hydrogen, modeled extensively, with fractures reaching 5 times deeper than Earth's. Carbon dioxide available in the ocean, confirmed by JWST in 2023. Sustained chemical gradients over geological time, guaranteed by tidal heating from the Laplace resonance. The only items that remain unconfirmed are the specific mineral composition of the vent chimneys and the pH gradient between vent fluid and ocean water. And those cannot be confirmed without going there. Every checkable box has been checked. But here is what Lane's work, as compelling as it is, does not quite do. It explains how life could have started at alkaline vents on a world like Europa. It makes the chemistry plausible. It makes the energy budget work. But it does not tell you that it had to happen. It tells you the conditions are right. It does not tell you the outcome is compelled. To get there, you need a different kind of argument. You need thermodynamics. And you need to be willing to follow thermodynamics to a conclusion that most people find deeply uncomfortable. In 1977, a Belgian physical chemist named Ilya Prigogine won the Nobel Prize in Chemistry for work he had been developing since the 1940s. Prigogine was born in Moscow in 1917, months before the Russian Revolution, to a Jewish family that fled first to Germany and then to Belgium. He became a naturalized Belgian citizen, studied chemistry at the Université Libre de Bruxelles, and eventually held positions there and at the University of Texas at Austin, where he founded the Center for Statistical Mechanics. He died in 2003. His major insight was that thermodynamic systems driven far from equilibrium do not simply decay toward maximum entropy. They can spontaneously self-organize into ordered structures maintained by continuous energy dissipation. He called these dissipative structures. The classic example is a Bénard convection cell. Heat a thin layer of fluid from below. At a critical temperature gradient, the fluid does not just conduct heat randomly. It organizes into hexagonal convection cells, a highly ordered pattern. maintained by the continuous flow of energy through the system. The order is not imposed from outside. It emerges from the thermodynamics. Prigogine showed this was not a special case, but a general principle. Systems far from equilibrium are not just permitted to self-organize. Under the right conditions, self-organization is the thermodynamically favored state. Europa's ocean is a textbook far from equilibrium system. Energy flows in from two directions: radiation-driven chemistry from above, serpentinization-driven chemistry from below. The ocean sits between these two energy sources, like the fluid in a Bénard cell sits between the hot plate and the cold surface. Prigogine's framework says that in such a system, the spontaneous emergence of organized structures is not surprising. It is expected. But Prigogine was talking about convection cells and chemical oscillations. He was not talking about life. The jump from Bénard cells to biology is enormous, or at least that is what people assumed until a young physicist at MIT published a paper in 2013 that made a very different argument. Jeremy England was 31 years old when he published Statistical Physics of Self-Replication in the Journal of Chemical Physics. He had a bachelor's degree in biochemistry from Harvard, a Rhodes Scholarship to Oxford, and a PhD in physics from Stanford. He was an assistant professor at MIT, and his paper made a claim so sweeping that a writer in Quantum magazine compared him to the next Darwin, a comparison England himself would later try to walk back. England's argument starts with a result from non-equilibrium statistical mechanics called the Crookes fluctuation theorem, which relates the probability of a thermodynamic process occurring forward versus in reverse. England applied this to groups of molecules driven by external energy sources and derived a mathematical relationship showing that such groups will tend to self-organize into configurations that are better at absorbing and dissipating the energy driving them, not because they are trying to, not because anything is directing them, because the second law of thermodynamics, combined with the specific mathematics of driven systems, makes those configurations more likely to persist. Self-replication, England argued, is an exceptionally effective energy dissipation strategy. If you are a collection of molecules being driven by an energy source, one extremely efficient way to dissipate more of that energy is to make more copies of yourself. Each copy is another dissipator. The system ratchets toward greater complexity because complexity dissipates more energy, and thermodynamics favors states that dissipate more energy in driven systems. England's own framing was carefully provocative. He suggested that the origin of life should be as unsurprising as rocks rolling downhill. Quantum magazine ran the piece in 2014 under the headline "A New Physics Theory of Life," and the reaction from the scientific community was immediate and divided. Some physicists called it brilliant. Others said it was too general, that it explained why matter self-organizes, but not why it self-organizes into the specific molecular machinery of life. An open fire dissipates energy efficiently, but an open fire is not alive. England was describing a thermodynamic tendency, not a mechanism. The tendency was real, but the specifics were missing. In 2017, computational work by Tal Kachman, Jeremy Owen, and England himself, published in Physical Review Letters, provided some of those specifics. They simulated chemical networks driven by external energy and showed the systems spontaneously evolved toward configurations that were not just good at dissipating energy, but were fine-tuned for it. landing in the 99th percentile of forcing effects. The simulations showed something like natural selection emerging from raw physics, without any biology, without any genetic code, without any replication at all. Just thermodynamics doing what thermodynamics does. England eventually left MIT. He moved to Georgia Tech as a principal research scientist, then to Bar Ilan University in Israel as a visiting professor. He co-founded a company called Conquest Labs in 2025. His book, Every Life is on Fire, came out in 2000. He was cautious in interviews, more cautious than his supporters. I am not saying this tells me a lot about what is going on in a biological system, he said in one, nor even claiming that this is necessarily telling us where life as we know it came from. But the mathematical result stands. In driven systems, self-organization is thermodynamically favored. The universe does not need a reason to build complexity. It needs a reason not to. And England was not alone. He was not even first. Stuart Kauffman, born in 1939, a MacArthur Fellow and longtime member of the Santa Fe Institute, had been making a version of this argument since 1971. Kauffman's framework is different from England's. Where England works from non-equilibrium statistical mechanics, Kauffman works from network theory and random graph mathematics. His concept is the autocatalytic set, a network of chemical reactions in which every molecule's formation is catalyzed by some other molecule in the network. The network sustains itself. No single molecule needs to self-replicate. The network as a whole is the replicating unit. Kauffman showed, using random graph theory, that as chemical diversity increases in a system, the probability of autocatalytic closure, the probability that every reaction in the set is catalyzed by something else in the set, undergoes a phase transition. Below a critical threshold of diversity, autocatalytic sets are vanishingly unlikely. Above it, they are almost certain. The transition is sharp, like water freezing or a magnet aligning. Kauffman's claim, developed across 3 decades and multiple books including The Origins of Order in 1993, At Home in the Universe in 1995, and A World Beyond Physics in 2019, is that life is an expected, collectively self-organized property of catalytic polymers, not an accident, a phase transition. Then there is Robert Hazen, a mineralogist at the Carnegie Institution for Science. Hazen published a paper in PNAS in October 2023, co-authored with Michael Wong, Carol Cleland, Jonathan Lunine, and others, proposing what he explicitly called a new law of nature. The paper's title was On the Roles of Function and Selection in Evolving Systems, and its claim was that any system with many possible configurations that undergoes selection for function will evolve toward greater complexity, not just biological systems, any system, minerals, stars, atmospheres, chemistry. Hazen pointed out that Earth started with roughly 20 primordial mineral species and now has over 5,900, an explosion of mineral diversity driven by the same principle he was describing. He called it a second arrow of time, running alongside entropy increase, but in the opposite direction, toward complexity rather than disorder. The word Hazen used was law, not hypothesis, not framework, law. And Jonathan Lunine, one of the co-authors, is a planetary scientist at Cornell whose specialty is the outer solar system. His involvement was not coincidental. The implications for Europa were baked into the paper from the start. Then there is Lee Cronin, And this is where the story gets complicated, because Cronin is the most controversial figure in this entire constellation of ideas. Cronin holds the Regius Chair of Chemistry at the University of Glasgow and has developed, along with Sarah Walker at Arizona State University, something called assembly theory. The core idea is that you can measure the complexity of a molecule by counting the minimum number of bond-forming steps required to build it from basic building blocks. This number is called the assembly index. Cronin and Walker's empirical finding, validated using mass spectrometry on blind samples including extraterrestrial material, is that molecules with an assembly index of 15 or higher found in high abundance have only ever been observed in samples of biological origin. Below 15, abiotic chemistry can produce them. Above 15, in high copy numbers, only life does. The potential application to Europa is direct. A mass spectrometer, which is exactly what Europa Clipper carries, could analyze material from Europa's surface or from a plume, measure the assembly indices of the molecules it finds, and determine whether those molecules cross the threshold. The method is agnostic. It does not assume Earth-like biochemistry. It does not require you to know what Europa's life looks like. It just counts complexity. But the backlash has been fierce. When Cronin and Walker published Assembly Theory Explains and Quantifies Selection and Evolution in Nature in October 2023, evolutionary biologists reacted with outrage. Some called it nonsense. Others called it a Trojan horse for creationism, an accusation Cronin found baffling. Hector Zenil at King's College London argued the assembly index was mathematically equivalent to already known complexity measures, just repackaged with new terminology. Robert Hazen's own group demonstrated that abiotic crystal structures could exceed the assembly index threshold of 15, directly challenging the biosignature claim. And in 2002, the Royal Society of Chemistry suspended Cronin for 3 months for breaching their code of conduct, though the specifics of that case are separate from the science. Cronin's response has been defiant. Could the theory be wrong? Possibly. That is the point and the case for all theories. But perhaps it is less wrong than our current understanding. Sarah Walker, for her part, published a book in 2004 called Life as No One Knows It, arguing that current physics is fundamentally insufficient to explain life, that a new physics is needed to capture how information and selection shape the material world. Walker is not a fringe thinker. She is a professor at ASU's School of Earth and Space Exploration, deputy director of the Beyond Center for Fundamental Concepts in Science, and a recipient of the Stanley Miller Early Career Award and the Schmidt Sciences Polymath Award. And there are more. Adi Pross at Ben Gurion University proposed dynamic kinetic stability, a framework arguing that replicating systems obey a different kind of stability than static objects, one where greater stability is associated with greater reactivity. Eric Smith and Harold Morowitz at the Santa Fe Institute argued that life's core biochemistry is a relaxation channel driven into existence by geochemical free energy, that the emergence of life is a non-equilibrium phase transition. Christian de Duve, who won the Nobel Prize in 1974, coined the phrase cosmic imperative in his 1995 book, Vital Dust, arguing that life is not chance, but law. Paul Davies, Regents Professor of Physics at Arizona State and winner of the Templeton Prize, has spent decades in this territory. In his 1990 book, The Fifth Miracle, he reported that many scientists fervently conclude that the laws of nature are, to put it bluntly, rigged in favor of life. In The Demon in the Machine, published in 2019 and named Physics World's Book of the Year, he argued that living organisms act as informational Maxwell's demons, creating order from chaos. His position is nuanced. He does not think known physics is sufficient to explain life. He thinks a new kind of law is needed, one that fast-tracks complex matter toward life. 7 frameworks, 7 independent research programs, different mathematical tools, different disciplines, different institutional affiliations, and in some cases, researchers who actively disagree with each other on the details. Cronin and Hazen have clashed publicly. England and Kaufman approach the problem from opposite ends. Walker and Davies agree on the need for new physics, but disagree on what that physics looks like. These are not people coordinating a narrative. They are people who independently arrived at overlapping conclusions, and the overlap is the part that should disturb you, because what they converge on is this: given a thermodynamic system far from equilibrium, with liquid water, dissolved carbon, a sustained source of chemical energy, and sufficient time, the emergence of complex, self-organizing chemistry is not a matter of probability. It is a matter of physics. The specific frameworks disagree about the mechanism. They disagree about whether you need new laws or whether the existing laws suffice. They disagree about whether the result is replicating life or merely complex chemistry that resembles life. But they agree on the direction. Complexity is not accidental. It is driven. If even half of these frameworks survive the next decade of peer review, the implication is not that Europa might harbor life. The implication is that Europa has been doing what the universe always does when you give it the right conditions. And the only thing that has been missing is someone willing to look. And that is exactly what we built. And the story of how we almost did not build it is in its own way as disturbing as anything happening inside Europa's ocean. Europa Clipper is the largest spacecraft NASA has ever built for a planetary mission. With its solar arrays deployed, it spans over 30 meters, about 100 feet, roughly the length of a basketball court. It weighs approximately 6,605 kilograms. It carries 9 scientific instruments designed to interrogate every aspect of Europa's ice shell, ocean, and surface chemistry. It launched on October 14, 2004, from Kennedy Space Center aboard a SpaceX Falcon Heavy. And right now, as you hear this, it is somewhere in the inner solar system, having completed a gravity assist flyby of Mars on March 1st, 2025, heading toward an Earth gravity assist in December of 2026, before finally entering Jupiter's orbit on April 11th, 2030. Its primary science mission begins in the spring of 2031. 49 close flybys of Europa, some as close as 25 kilometers above the surface. $5 billion, 5.5 years of transit, 49 chances to taste what Europa's ocean is made of. And the whole thing almost never happened, not because the technology was impossible, not because the science was uncertain, because the people who control the money decided it was not worth building. After the Galileo spacecraft confirmed Europa's ocean in 2000, a series of mission concepts rose and died over the following decade and a half. The Europa orbiter was too expensive. The Jupiter Icy Moons Orbiter a $16 billion nuclear-powered concept, was cancelled when its budget became indefensible. The Jupiter-Europa orbiter, at $4.3 billion, was killed when the 2011 Planetary Science Decadal Survey, the document that sets NASA's priorities for a decade, chose Mars sample return instead. Europa lost to Mars. Again, JPL engineers redesigned the concept. Instead of orbiting Europa inside Jupiter's crushing radiation belts, the spacecraft would orbit Jupiter and make repeated close flybys. The radiation exposure per encounter would be manageable. The cost came down to roughly $2 billion. It was elegant, feasible, and scientifically compelling. And in 2013, the Obama administration's budget request stated explicitly, in writing, that the budget does not and cannot, at this time, accommodate any mission to orbit or land on Jupiter's moon, Europa. The mission was dead. What happened next is one of the strangest stories in the history of space exploration, because the mission was resurrected not by NASA, not by the scientific community, but by a single United States congressman from Houston, Texas, named John Culberson. Culberson represented Texas's 7th congressional district from 2001 to 2019. He had a law degree and a genuine, almost obsessive passion for space science. He had read Arthur C. Clarke's 2010 as a teenager and never recovered from the line, "All these worlds are yours, except Europa. Attempt no landing there." Starting in fiscal year 2013, before NASA had committed to the mission, before there was even an official project, Culberson began adding money to NASA's budget, specifically earmarked for Europa exploration. The numbers tell the story. In fiscal year 2013, NASA requested $0 for Europa. Congress provided $75 million. In 2015, NASA requested $15 million. Congress provided $100 million. In 2017, NASA requested $49.6 million. Congress provided $275 million. By 2019, Congress was providing $545 million for Europa Clipper and an additional $195 million for a lander concept that NASA had never asked for. Culberson became chairman of the House Appropriations Subcommittee that controls NASA's budget in January 2015, and he used that position with a focus that bordered on single-mindedness. He visited JPL regularly. He passed scientific papers around during budget markups. He once told a hearing, "We will only have one chance at this in our lifetime. We have only one shot. I want to be sure that we are here to see the first tube worms and lobsters on Europa." The Planetary Society, the space advocacy organization founded by Carl Sagan, mobilized citizens behind the effort. Between 2013 and 2016, they generated 384,949 messages to Congress and the White House in support of the Europa mission. Bill Nye, the organization's CEO, discussed Europa with President Obama aboard Marine One in 2015. But there was a cost. Culberson's Europa obsession became a political vulnerability. The Houston Chronicle, his hometown newspaper, endorsed his opponent in the 2018 midterm election, writing that he seems to care a bit more about the water on Europa than he does the water in the Addicks and Barker dams, a reference to Houston's catastrophic flooding during Hurricane Harvey. A political action committee ran attack ads declaring, "John Culberson's ideas are out of this world. He wanted NASA to search for aliens on Europa." He lost his re-election race in November 2018 to Democrat Lizzie Fletcher. The Planetary Society wrote that his motivation was passion, not parochialism, and that without John Culberson, none of this would have happened. The man who saved the Europa mission was voted out of office for saving it. He will almost certainly never see the results. Europa Clipper's prime science mission does not begin until 2031. Its data will take years to fully analyze. Whatever the spacecraft finds, John Culberson will experience it as a private citizen watching from Houston, if he is watching at all. That is the cost of doing something that matters on a timeline longer than an election cycle. The mission survived Culberson's departure because by then it had institutional momentum. But it nearly died again in 2024, just months before launch, for a reason so banal it feels like a cosmic joke. In May of 2024, an engineer at JPL attended a conference and learned that a type of transistor manufactured by Infineon Technologies, a MOSFET used extensively in electronics, was failing at lower radiation doses than expected. Infineon had quietly changed its manufacturing process without notifying NASA. Roughly 1,500 of these transistors were embedded throughout Europa Clipper's electronics vault, which had been sealed shut in October of 2023. The vault is the spacecraft's radiation shield, a custom-built box of aluminum and zinc designed to protect the electronics from Jupiter's radiation, and the electronics inside it were now potentially vulnerable to the very thing the vault was designed to stop. For 4 months, teams at JPL, Johns Hopkins Applied Physics Laboratory, and NASA Goddard ran around-the-clock tests, irradiating spare transistors, modeling thermal environments, simulating the cumulative radiation dose across the entire mission timeline. The question was binary. Could the transistors survive Jupiter or not? If not, the mission was over. You cannot open the vault. You cannot replace 1,500 transistors scattered across dozens of circuit boards. You fly with what you have, or you do not fly. The answer came on September 4th, 2024, roughly 6 weeks before the planned launch. Jordan Evans, the project manager, announced that engineers had determined the transistors would self-heal through thermal annealing during the approximately 20-day intervals between high radiation flyby encounters. The radiation damage would accumulate during each close pass, but in the weeks between passes, as the spacecraft retreated from Jupiter's inner magnetosphere, the transistors would recover. The margin was not generous, but it was sufficient. Evans declared, "High confidence we can complete the original mission for exploring Europa as planned." The launch proceeded on October 14th after a 4-day delay caused by Hurricane Milton. So the spacecraft is in space. It is healthy. It is en route, and the instruments it carries are, in terms of sensitivity, the most capable astrobiological toolkit ever sent to the outer solar system. 2 of those instruments matter most for the question this script has been building toward. The first is called SUDA, the Surface Dust Analyzer, built by Sasha Kemp's team at the University of Colorado Boulder. SUDA is a time-of-flight mass spectrometer with a gold-coated sensor head that captures individual ice grains and dust particles ejected from Europa's surface by micrometeorite impacts. When a particle hits the sensor at hypervelocity, it vaporizes and ionizes, and SUDA reads the mass spectrum of what is left. It can detect amino acids at concentrations of roughly 1 part per million. It can detect DNA nucleobases at similar sensitivities. A 2004 paper by Fabian Klenner and colleagues demonstrated that SUDA could identify biosignatures from less than a single bacterial cell's worth of material in a single ice grain, compared to the cosmic dust analyzer on Cassini, which analyzed the plumes of Enceladus with roughly 30 to 300 individual grain impacts per fly-through. SUDA is expected to capture 10,000 to 100,000 grains per encounter, with 4 times better mass resolution. The second is MassSpex, the mass spectrometer for planetary exploration, developed at the Southwest Research Institute. MassSpex is a neutral gas mass spectrometer with a mass resolution of up to 50,000, which is 50 times better than any mass spectrometer previously flown in space. It carries a cryogenic trap that accumulates volatiles during flybys, boosting its sensitivity by more than 1,000-fold. MassSpex can detect trace gases at parts per trillion for noble gases and subparts per million for organic compounds, including alkanes, alcohols, amines, nitriles, and amino acid fragments. If Europa's ocean contains molecules with assembly indices above 15, if Cronin and Walker's threshold holds, then SUDA and MassSpex have the sensitivity to detect them, not by looking for specific Earth-like biomolecules, by looking for molecular complexity itself. The measurement is agnostic. It does not care what Europa's chemistry looks like. It counts the steps required to build what it finds. But here is the tension that nobody in the astrobiology community can resolve, and it is the tension the script has been building towards since the beginning. The assembly theory threshold is already under attack. Hazen's group showed abiotic crystals can cross it. Zenal argues the mathematics is not new. The 2024 Juno revision of Europa's oxygen production rate downward to 12 kilograms per second, roughly a factor of 20 to 100 below earlier upper bound estimates, narrows the energy budget that was once thought to be so generous. The plumes that would give SUDA and MassSpex the cleanest possible sample, direct ocean material ejected into space, have been detected by Hubble 3 separate times and by Galileo once, but JWST found nothing during its 22,000 observations. The plumes appear to be real but intermittent. Europa Clipper's UVS ultraviolet spectrograph, built by Kurt Rutherford's team at the Southwest Research Institute, is designated the mission's plume finder and achieved first light in May of 2025. But there is no guarantee the plumes will be active during the flyby windows. So the picture is this. 7 theoretical frameworks say that what Europa's ocean has been doing for 4 billion years is not random, that the physics compels complexity, that the emergence of self-organizing chemistry is written into the thermodynamic structure of the universe. But those frameworks are contested, incomplete, and have never been tested on another world. The most sensitive instruments ever built for this purpose are currently en route, but the specific detection framework that would provide the cleanest test is itself under fire. The energy budget may be tighter than we thought, and the sample delivery mechanism may not cooperate. We are closer than we have ever been to answering the central question, and the answer may still elude us, not because the universe is hiding something, but because the question is harder than any instrument can resolve in a single mission, and the willingness to fund the next one is never guaranteed. Think about what that means. We are a species that has identified the most promising place in the solar system to test whether life is a law of physics or an accident. We have built a machine capable of performing that test. We almost did not build it because we could not agree it was worth the money. A single politician saved it and lost his job. A manufacturing defect nearly killed it. And the theoretical framework that would give the answer its deepest significance is being torn apart in academic journals, even as the spacecraft that could validate it crosses the inner solar system. This is not how you treat the most important question in the history of your species. This is how you treat a hobby. And yet, the spacecraft is in flight. The instruments are operational. The trajectory is nominal. And in about 5 years, give or take, a machine built by a species that has only known about Europa's ocean for 25 years will begin tasting ice grains ejected from the surface of a world that has been running its chemistry for 4 billion. There is a version of this story that ends with the data, with mass spectra and assembly indices and confidence intervals, with papers in Nature and press conferences at NASA headquarters and carefully worded statements about the significance of the findings. That version is clean, procedural, and totally inadequate because it treats the question as a scientific problem. It is not a scientific problem. It is a mirror. Consider what it means if the answer is yes. Not, yes, we found interesting organic molecules. Not, yes, the data are consistent with prebiotic chemistry. The strong yes, the one the 7 frameworks are pointing toward. The one where Europa Clipper finds molecular complexity above the assembly threshold, or detects metabolic byproducts, or identifies chemical networks that could only have been produced by something that reproduces and evolves. The one where the data, after years of analysis and debate and replication, converge on the conclusion that life arose independently in Europa's ocean, that it is not Earth life, that it has a different origin, different biochemistry, different architecture. If that happens, and it may not, and the honest answer is that we do not know, but if it happens, then the story you were told about yourself collapses. The story where life on Earth was special, where the conditions that produced you were so improbable that they constitute a kind of secular miracle, where the universe is vast and mostly dead, and you exist against astronomical odds in a tiny pocket of warmth and water and luck. That story has been the foundation of how human beings think about themselves for as long as we have known about the scale of the cosmos. It is the story that makes life feel precious. It is the story that makes you feel rare. And it is the story that every one of the 7 frameworks we discussed says is probably wrong. Because if life is not an accident but a consequence of thermodynamics, then you are not rare. You are typical. You are what matter does when energy flows through it for long enough. The way hurricanes are what atmospheres do when temperature gradients persist. The way stars are what hydrogen does when gravity has its way. You are not the exception to the universe's dead indifference. You are the rule, and the rule applies everywhere the conditions hold. Europa's ocean is one such place. Enceladus is another. Titan may be a third, and those are just the worlds in our solar system. The galaxy contains roughly 100 billion stars, and current estimates suggest that at least a quarter of them host rocky planets in habitable zones. If you add the moons of gas giants, the number of potential ocean worlds is staggering. And if the 7 frameworks are right, every one of those worlds with liquid water, chemical energy, and sufficient time is doing what Europa is doing. Building. Not maybe. Not sometimes. Always. because the physics demands it. Robert Pappalardo has spent 30 years studying icy moons and 20 years building the Europa mission. He was inspired to pursue planetary science by Carl Sagan. As a student at Cornell, he chose the university specifically because Sagan taught there. He audited Sagan's classes. He presented research results to Sagan himself before Sagan's death in 1996. I would not be doing what I am today without Carl's influence, Pappalardo has said. Now, as Europa Clicker's project scientist, he carries the intellectual lineage of a man who spent his career arguing that the universe is more hospitable to life than most scientists were willing to admit. Sagan died 30 years ago. He never saw the JWST carbon detection. He never saw the sodium chloride discovery. He never saw assembly theory or dissipation-driven adaptation or the Hazen framework for functional information. He never saw a congressman from Texas risk his career to send a spacecraft to Europa. But the thread runs from his classroom at Cornell to the instrument vault on a spacecraft currently crossing the solar system. And that thread is not poetic. It is personnel. It is funding lines. It is specific human beings who chose to spend their careers on a question that most of their colleagues considered too speculative to take seriously. Margaret Kivelson confirmed Europa's ocean in the year 2000. She was 71 years old. She had earned her PhD under Julian Schwinger, the only woman he ever advised. She had spent decades studying magnetic fields and plasma physics. The Europa discovery was the capstone of a career that spanned almost the entire space age. And now, at 97 years old, she is the magnetometer team leader on Europa Clipper. She will be over 100 when the prime science mission begins. The best part, she has said, is that there is more to come. Brittany Schmidt, the scientist who proposed the shallow water lens model for Europa's chaos terrain, has been building a robot to explore under ice. It is called IceFin, a 12-foot tube-shaped autonomous underwater vehicle designed for deployment through ice. She has sent it under Antarctica's Ross Ice Shelf and through 600 meters of ice to the grounding line of the Thwaites Glacier, one of the most inaccessible environments on Earth. Time magazine named her one of the 100 most influential people of 2230. Her goal is explicit. She is building a prototype for a machine that could one day melt through Europa's ice shell and swim in the ocean below. She describes the work as exploring the hardest environment you can imagine, the most like Europa. That machine does not exist yet. The ice shell is 29 kilometers thick. Current technology cannot get through it. But the fact that someone is already building the tools, already testing them in the closest analog environments Earth offers, tells you something about what the people closest to this data believe they are going to find. 4 billion years. That is how long Europa's ocean has been sitting in the dark, fed by energy from a planet that does not know it is feeding anything, cycling chemistry through a system that does not know it is a system. 4 billion years is not a long time to wait for an accident. 4 billion years is a long time for a law of physics to run uninterrupted. And here is the thing about laws of physics. They do not care whether you are comfortable with what they produce. Gravity does not ask permission before collapsing a star. Entropy does not negotiate. If the thermodynamic frameworks are right, if Prigogine and England and Kaufman and Hazen and Walker and Lane and Davies are pointing at the same truth from different angles, then what Europa's ocean has been doing for 4 billion years is not something that requires explanation. It is something that requires a reason not to have happened. The burden of proof is inverted. You do not need to explain why there would be complex chemistry in Europa's ocean. You need to explain why there would not be. Nobody has offered that explanation. Nobody has even attempted it. The closest anyone has come is to say the frameworks are too new, too contested, too theoretical to draw conclusions. And that is true. They are. Assembly theory's biosignature threshold may not hold. England's dissipation argument may not bridge to actual biology. Kaufman's phase transitions may not occur in real geochemistry the way they occur in mathematical models. Every framework has vulnerabilities. Every framework has critics. The honest position is uncertainty. But uncertainty is not the same as improbability. And the direction of the evidence, the convergent direction of 7 independent programs, is not toward Europa's ocean is probably dead. It is toward something else entirely. Something that the careful language of scientific papers is not designed to express, because scientific papers are designed to state what you know, not what the trajectory of accumulating knowledge implies. What it implies is that we are not looking at a question anymore. We are looking at an answer that nobody is ready to say out loud. Kevin Hand, the astrobiologist at JPL, who has dived to the bottom of the Mariana Trench and camped on Antarctic glaciers and spent 2 decades thinking about Europa's ocean, wrote in his 2020 book Alien Oceans that if life is found on Europa, it would mean perhaps our tree of life, the singular center of biology as we know it, is revealed to be but a tiny twig on a tiny branch joined to a vast and grand tree of life, connecting the beauty of all life in the known universe. That sounds almost hopeful when you read it. A grand tree, a connected beauty. But think about what it actually means. It means you were never the point. Earth was never the point. The particular accident of your DNA, your species, your civilization, your ability to build telescopes and mass spectrometers and spacecraft, all of that was one instance of a process that was always happening everywhere. You did not beat the odds. There were no odds to beat. You are what the universe does, and it does it in the dark, under ice, on a moon most people cannot find on a diagram of the solar system, with no audience and no purpose and no awareness that it is doing anything at all. So you have the chemistry, you have the energy, you have 7 independent theoretical frameworks built by people who mostly disagree with each other, and all 7 say the same thing. The universe, when you hand it certain conditions, does not sit around hoping something interesting will happen. It builds, and everything we know about Europa says those conditions have been running uninterrupted in total darkness for over 4 billion years. But knowing this and proving it are 2 completely different problems, because the frameworks are theoretical. The chemistry is modeled. The ocean is inferred from magnetic field variations measured during a flyby in January of 2000. Nobody has ever tasted Europa's water. Nobody has ever held a sample of what that seafloor is producing. Nobody has measured the assembly index of a single molecule from that ocean. And the distance between a theoretical prediction and an empirical confirmation is not small. It is the distance between a compelling argument and a fact. To cross that distance, you need an instrument. You need to go there, and the instrument we built to go there almost never existed. The story of Europa Clipper is not a story about engineering triumph. It is a story about how close the most important measurement in the history of science came to being cancelled by budget politics, manufacturing fraud, and hurricanes. And the reasons it almost failed tell you something deeply uncomfortable about how seriously human civilization takes the question of whether it is alone in the universe. Robert Pappalardo has studied icy moons for 30 years. He chose Cornell University for his undergraduate degree in geological sciences because Carl Sagan taught there. Pappalardo was not an astronomy student. He was in geology, but he audited Sagan's classes. He sat in the Uris Hall lecture room and listened to the man who had turned planetary science from a backwater into a cultural force. Before Sagan died of pneumonia in December of 1996, at age 62, Pappalardo had the chance to present his early Europa research to him directly. He later said that he would not be doing what he is doing today without Carl's influence. What he is doing today is serving as project scientist for Europa Clipper. The role is the culmination of 20 years of effort, not 20 years of building a spacecraft, 20 years of trying to convince the people who write the checks that the question is worth asking. Because after Galileo confirmed Europa's ocean in the late 1990s, Pappalardo and a generation of planetary scientists watched mission after mission get proposed, designed, costed, and killed. The Europa orbiter concept emerged in the late 90s. It was going to orbit Europa directly. Too expensive. Cancelled. The Jupiter Icy Moons Orbiter, an ambitious $16 billion nuclear electric propulsion concept that would have visited Callisto, Ganymede, and Europa, was announced by the Bush administration in 2003. By 2005, it was dead, a victim of cost overruns on the Project Prometheus nuclear program. The Jupiter Europa Orbiter, a more modest $4.3 billion concept developed jointly with ESA, was killed when the 2011 Planetary Science Decadal Survey recommended Mars sample return as the top priority instead. Each of these cancellations represented years of design work. Each time, the scientific case for Europa was stronger than before. Each time, someone decided the money was better spent elsewhere. JPL engineers, watching this parade of failures, redesigned the architecture from scratch. The insight was simple but transformative. The thing that makes Europa expensive to study is Jupiter's radiation. Orbiting Europa means sitting inside those radiation belts permanently. Your electronics cook. Your mission lifetime shrinks. Your shielding mass explodes. But what if you did not orbit Europa at all? What if you orbited Jupiter on a high elliptical path that dips down to Europa for brief flybys and then retreats to safer distances? You would spend most of your time outside the worst radiation. Each flyby would last only hours. Between flybys, your instruments cool down, your data downlinks, and your transistors heal. It was a flyby tour instead of an orbiter, and it brought the cost estimate down to roughly $2 billion. The concept was feasible, it was brilliant, and it still was not funded. In 2013, the Obama administration released a federal budget that contained a single relevant sentence. It stated that the budget does not and cannot, at this time, accommodate any mission to orbit or land on Jupiter's moon Europa. After everything Galileo found, after Margaret Kivelson's magnetometer confirmed a conducting ocean, after Kevin Hand and Steve Vance calculated that the chemical energy balance mirrors Earth's. The official position of the United States government was, "We are not going." That was the moment John Culberson entered the story. Culberson represented Texas's 7th Congressional District, which covers western Houston. He was a Republican. He had a law degree from South Texas College of Law. He had no formal scientific training, but he subscribed to science and nature. He read the Europa papers. He visited JPL and asked the engineers questions that surprised them with their specificity. And somewhere in that process, he decided that the question of whether life exists beyond Earth was the most important question a civilization could ask, and that failing to fund the mission capable of answering it was a moral failure. Starting in fiscal year 2013, the same year the administration said no, Culberson began inserting money into NASA's budget for Europa. Not money NASA requested, money Culberson decided NASA needed. In 2013, NASA requested zero for Europa. Congress, driven by Culberson, provided $75 million. In 2015, NASA requested $15 million. Congress provided $100 million. By 2017, NASA asked for roughly $50 million. Congress gave $275 million. Culberson did not do this quietly. He passed scientific papers to his colleagues during appropriations markups. He brought JPL officials to testify. He visited the clean rooms at the Jet Propulsion Laboratory so many times, the guards knew his name. In January of 2015, Culberson became chairman of the House Appropriations Subcommittee, responsible for commerce, justice, and science, the subcommittee that controls NASA's funding. That was the inflection point. With the gavel came the line items. By fiscal year 1910, Congress was providing $545 million for Europa Clipper, plus another $195 million for a lander concept study. The total appropriation far exceeded anything NASA had planned or requested. The Planetary Society, the nonprofit advocacy organization co-founded by Carl Sagan, mobilized public support at a scale rarely seen for a science mission. Between 2013 and 2016, the Society generated 384,949 individual messages to Congress and the White House advocating for a Europa mission. Bill Nye, the Society's CEO, discussed Europa with President Obama aboard Marine One in 2015. The campaign worked, but at its center, providing the political leverage that made all of it possible, was one congressman who believed the question mattered more than his career. He was right about the career part. The Houston Chronicle, his hometown newspaper, endorsed his Democratic opponent in the 2018 midterms. The editorial board wrote that Culberson seemed to care a bit more about the water on Europa than he did about the water in the Addicks and Barker dams, a direct reference to the catastrophic flooding that had devastated parts of Houston during Hurricane Harvey in 2017. A political action committee ran an attack ad with the following language: John Culberson's ideas are out of this world. He wanted NASA to search for aliens on Europa. Think about the contempt in that sentence. This is a man who read the peer-reviewed literature, visited the laboratory, consulted the scientists, and used his elected position to fund what those scientists said was the most important planetary science mission of a generation, and the political system punished him for it. Not because the science was wrong, because the optics were bad, because caring about an ocean on a moon of Jupiter looked frivolous next to flooding in Houston. He lost to Lizzie Fletcher by about 5 points. He has not held elected office since. The Planetary Society's post-mortem on his career stated that his motivation was passion, not parochialism, and that without John Culberson, none of this would have happened. That sentence should sit with you. The $5.2 billion spacecraft currently falling toward Jupiter exists because of one man's stubbornness and the institutional indifference of everyone around him. And the absurdity did not end with Culberson's defeat. Even after the money was secured, the mission got tangled in a launch vehicle fight that had nothing to do with science and everything to do with politics of a different kind. Culberson and Senator Richard Shelby of Alabama had mandated that Europa Clipper launch on the Space Launch System, NASA's massive and perpetually delayed heavy-lift rocket, built largely in Shelby's home state. SLS was behind schedule and wildly over budget. Every SLS core stage was spoken for years in advance, primarily for the Artemis lunar program. Assigning one to Europa Clipper meant either delaying Artemis or delaying Europa. Neither camp wanted to yield. The SLS requirement also inflated costs by an estimated $1.5 to $2 billion. The rocket's raw power would have sent Clipper on a direct trajectory to Jupiter in under 3 years, but the extra billions could have funded another entire mission. For 2 years, the Clipper team was forced to maintain dual compatibility with SLS and a commercial alternative simultaneously, an engineering headache that consumed resources, attention, and morale. In the 2001 Omnibus Spending Bill, Congress finally released Clipper from the SLS mandate. NASA directed the team to immediately cease efforts to maintain SLS compatibility. The switch to SpaceX's Falcon Heavy saved roughly $2 billion and freed the Artemis schedule. It also meant a longer journey. The new trajectory required gravity assists from both Mars and Earth, stretching the flight to 5.5 years instead of 2.5. Margaret Kivelson, already in her 90s when the decision was made, would have to wait 3 extra years for the data she had spent a quarter century anticipating. And even after Culberson won the funding war, even after the spacecraft was designed and built and tested and assembled in the JPL cleanroom, the mission nearly died a second time. In May of 2200, 5 months before the scheduled October launch window, a JPL engineer attended an electronics industry conference and learned that a specific model of MOSFET transistor manufactured by Infineon Technologies was failing under radiation at lower doses than the component's specifications promised. Infineon had changed its manufacturing process. They had not told NASA. Approximately 1,500 of these transistors were embedded throughout Europa Clipper's central electronics vault, the radiation-shielded core of the spacecraft's brain. The vault had been sealed in October of 23, 7 months before anyone found out the transistors might not work. You cannot reopen a spacecraft's radiation vault 5 months before launch and replace 1,500 transistors. The integration is too tight, the connections too numerous, the testing too extensive. The transistors were going to Jupiter regardless. The question was whether they would survive. For 4 months, 3 separate teams at JPL, Johns Hopkins Applied Physics Laboratory, and NASA Goddard ran parallel testing campaigns, many of them around the clock. They blasted sample transistors with radiation. They tracked degradation curves. They modeled thermal cycling. Europa's surface receives approximately 540 rem of radiation per day. The spacecraft's vault is heavily shielded, but over 49 flybys spanning 4 years, the cumulative dose adds up. If the transistors degraded faster than the original Infineon specifications, the spacecraft could lose its ability to process commands or store data mid-mission. On September 4, 2024, project manager Jordan Evans made the announcement. Testing showed the transistors would degrade under radiation, as feared, but would self-heal through a process called thermal annealing during the roughly 20-day quiet periods between Europa flybys. The spacecraft's own orbital mechanics would save it. The high elliptical orbit that JPL had designed to limit radiation exposure also provided recovery time. The mission was cleared. On October 14th, delayed 4 days from the original date because Hurricane Milton forced Kennedy Space Center to close, Europa Clipper launched aboard a SpaceX Falcon Heavy, but the measurement it was built to make may still not be clean, because the plumes that would deliver the freshest ocean material directly into Clipper's instruments may not be there when Clipper arrives. The detection history is maddening. In December of 2012, Lorenz Roth's team at the Southwest Research Institute used Hubble's STIS ultraviolet spectrograph and saw excess hydrogen and oxygen emissions above Europa's southern hemisphere, consistent with 2 water vapor plumes rising roughly 200 kilometers. Published in Science, December 2013. The detection was real, but right at Hubble's limits. In 2016 and 2017, William Sparks at the Space Telescope Science Institute used transit absorption against Jupiter's disk and found plume signatures in 3 out of 10 observations. His 2016 detection showed a plume about 100 kilometers high at the same equatorial location as an earlier detection and a Galileo thermal anomaly. In 2018, Shanzhe Jia reanalyzed Galileo magnetometer data and found that the spacecraft had apparently flown through a plume during a 1997 encounter without anyone noticing it for 20 years. Then, in November of 2022, JWST pointed its infrared instruments at Europa and found nothing. No plumes, no vapor, the most sensitive telescope in existence, staring at the place where plumes had been reported multiple times, and seeing only ice. The current scientific consensus is that Europa's plumes are probably real, but intermittent, erupting unpredictably and possibly from localized sources, not like Enceladus, where Cassini could fly through a continuous curtain of spray and scoop up material from the ocean below. Europa's eruptions, if they happen during Clipper's 4-year campaign, will be a matter of luck and timing. Clipper's ultraviolet spectrograph, Europa UVS, achieved first light during commissioning in May of 2025 and is the designated plume hunter, but finding a plume during any specific 30-minute flyby window is not guaranteed. Without plumes, Clipper relies on what micrometeorite impacts kick off the surface, tiny grains of ice lofted by the constant bombardment of interplanetary dust drifting up into Europa's tenuous exosphere, where SUDA can catch them. The Surface Dust Analyzer, built by Sascha Kempf's team at the Laboratory for Atmospheric and Space Physics at the University of Colorado Boulder, is a time-of-flight reflectron impact ionization mass spectrometer. It captures individual ice grains that hit a gold-coated sensor plate at speeds of several kilometers per second. The impact vaporizes and ionizes the grain. The ions are sorted by mass. The chemistry is red. SUDA's resolution is roughly 4 times better than Cassini's cosmic dust analyzer. Its sensitivity has been tested in laboratory conditions by Fabian Klenner at the Free University of Berlin in a 2204 paper published in Science Advances. Klenner's team demonstrated that a mass spectrometer with Suda's specifications can detect amino acids at roughly 1 part per million concentration. It can identify lipid fragments. It can recognize DNA nuclear bases. And the number that should stay with you is this. Their testing showed that material from fewer than one bacterial cell distributed in a single ice grain would produce a detectable signal. One cell, one grain. To understand why that sensitivity matters, think about what Cassini found at Enceladus, with instruments that were 4 times less precise. In 2017, Hunter Waite's mass spectrometer detected molecular hydrogen in Enceladus's plume, direct chemical evidence of hydrothermal reactions on the seafloor. In 2018, Frank Postberg's cosmic dust analyzer found macromolecular organic compounds, large carbon-bearing molecules with masses above 200 atomic mass units, dissolved in the plume's ice grains. In 2023, Postberg's team found phosphates, completing the set of biologically essential elements. Cassini was not designed to search for life. It was a Saturn Systems survey mission launched in 1997 with 1990s technology, and it found the building blocks of biology spraying into space from a moon nobody expected to be interesting. SUD and MassSpecs were designed from the ground up to do what Cassini stumbled into. They are a generation ahead in sensitivity. They have the resolution to distinguish between biotic and abiotic organic signatures, and they are heading to an ocean that is roughly 50 times larger than Enceladus's, has existed far longer, and sits atop a rocky seafloor with a far greater surface area for water rock chemistry. If Enceladus gave us the building blocks with instruments that were not even looking, what will Europa give us with instruments that are? MASPX, the mass spectrometer for planetary exploration, is even more sensitive in a different way. Developed at the Southwest Research Institute under the leadership of Hunter Waite, the same scientist whose instrument found molecular hydrogen in Enceladus's plume, MASPX analyzes neutral gas rather than solid particles. It uses a multi-bounce time of flight architecture that gives it a mass resolution of 50,000 at full width, half maximum. That is 50 times better than any mass spectrometer ever flown in space. A cryogenic trap accumulates volatiles during each flyby, concentrating the sample by more than 1,000 times. MASPX can detect trace organics at parts per billion. It can distinguish between amino acids, lipids, and nuclear bases. If Europa's exosphere contains even a whisper of complex organic chemistry from the ocean below, MASPX will see it. And now bring this back to Lee Cronin. Assembly theory, the assembly index. The claim that molecules requiring 15 or more sequential bond-forming steps for their construction, found in high copy numbers, are overwhelmingly likely to be products of life or lifelike processes. You measure the assembly index through mass spectrometry. You fragment the molecule and reconstruct its minimum assembly pathway. SUDA and MassSpecs can do exactly this. If Clipper catches ice grains or exospheric gas containing complex organic molecules from Europa's ocean, and those molecules show assembly indices above 15 in high abundance, it would constitute the first off-Earth empirical test of whether Europa's chemistry has crossed from random soup into directed construction, from noise into signal, from accident into law. But the threshold itself is under fire. Robert Hazen's group demonstrated in 2204 that certain abiotic crystal structures can produce molecules exceeding assembly index 15 without any biology. If non-living processes can cross the line does not mean what Cronin claims it means. Cronin disputes this interpretation. Hazen's team stands by their results. The debate is published, peer-reviewed, and entirely unresolved, which means the specific interpretive framework that would give Clipper's most important data its clearest meaning is itself an active scientific controversy. Even if Suda catches the perfect molecule, the argument about what it means could outlast the mission, so the plumes might not show up. The transistors were manufactured wrong. The interpretive framework is contested. The mission was nearly cancelled by budget politics, and the man who saved it was voted out of office for his trouble. This is the state of humanity's best attempt to answer the most important question it has ever formulated. And despite everything, it is more than we have ever had. It is closer than we have ever been. And here is what nobody in the official communications will say. If the inevitability thesis is correct, if the converging frameworks are even approximately right, then the question was never whether Europa's ocean contains something interesting. The question is what it contains after 4 billion years of uninterrupted operation. 4 billion years. Think about what that number means by comparison. On Earth, 4 billion years of energy flowing through chemistry produced everything, every organism that has ever lived, every cell that has ever divided, from the first archaea clustering around alkaline vents to the blue whale and the brain reading these words. And Earth's process was interrupted constantly. Asteroid impacts that boiled the oceans, snowball glaciations that froze them, mass extinctions that wiped out 70 to 96% of all species, 5 separate times. Europa's process was never interrupted. The Laplace resonance that drives tidal heating has been stable for billions of years. The serpentinization at the seafloor runs as long as water touches rock, and the rock contains iron. The radiolytic cycle on the surface runs as long as Jupiter's magnetosphere exists, which is as long as Jupiter exists. There were no asteroid impacts punching through an ice shell tens of kilometers thick, no glaciations to reset the chemistry, no mass extinctions, just water, rock, energy and time, unbroken, undisturbed. 4 billion years in the dark. There is a version of this where you find that comforting, where you frame it as meaning life is resilient and universal and woven into the fabric of existence. Kevin Hand, who dove to the bottom of the Mariana Trench with James Cameron and has spent decades studying the extremes of Earth's biosphere to prepare for the extremes of alien ones, described what confirming life on Europa would mean. He said perhaps our tree of life, the singular center of biology as we know it, is revealed to be but a tiny twig on a tiny branch joined to a vast and grand tree of life, connecting the beauty of all life in the known universe. That is the generous reading. That is the reading where being common makes you part of something magnificent. But follow the logic one more step. If the tree grows everywhere the physics allows, then it is not a grand tree. It is an automatic tree. A tree the universe did not decide to grow. A tree that grows because not growing would violate a thermodynamic principle, the same way heat not flowing downhill would violate one. The tree does not know it is a tree. The branches do not know they are branches, and the process that made you does not know it made you. It did not intend you. You are not the purpose. You are the byproduct, a side effect of the universe managing its entropy budget on the way to heat death. The second law of thermodynamics says isolated systems evolve towards maximum disorder. But these frameworks say something more specific. They say that on the way to maximum disorder, the universe is required to pass through phases of increasing complexity. Stars ignite, planets differentiate, chemistry organizes, and somewhere in that mandatory passage between the low entropy of the Big Bang and the heat death of everything, the universe builds structures that are capable of asking why they exist. Not because the question matters to the universe, but because building the structures that ask the question is thermodynamically favored. You are what happens when a gradient dissipates efficiently. The question you are asking right now, what is in that ocean, is itself a product of the same process you are asking about. Margaret Kivelson was 28 years old when she began her doctorate under Julian Schwinger, who would win the Nobel Prize for quantum electrodynamics. She was the only woman he ever supervised. She was 71 when her magnetometer data confirmed Europa has a subsurface ocean. She is 97 now, still on the Europa Clipper team as magnetometer lead. She will be 102 when the first science data comes back in 2031. When asked about the timeline, she said the best part is that there is more to come. Brittany Schmidt was a physics undergraduate at the University of Arizona when she first became fascinated by ice. She earned her PhD in geophysics from UCLA, studying Europa's ice shell dynamics. In 2011, she published a paper in Nature proposing that Europa's chaotic terrain forms over shallow water lenses just 3 kilometers below the surface. Bodies of liquid water, the size of the Great Lakes, trapped within the ice shell itself. The idea elegantly resolved a debate that had paralyzed the field for years. Then she did something most planetary scientists never do. She went to Antarctica and built a robot to test the idea. Icefin is a 12-foot-long torpedo-shaped underwater vehicle designed to operate beneath ice shelves. Schmidt's team deployed it under the Ross Ice Shelf and at the grounding line of the Thwaites Glacier, drilling through 600 meters of Antarctic ice to reach the ocean below. Icefin mapped the underside of the ice, measured water chemistry, and filmed environments that no human had ever seen. Schmidt was named one of Time's 100 most influential people of 2003. Her stated purpose is explicit. She is building the technology that will one day swim beneath Europa's ice. She said they are trying to explore underwater, under ice, the hardest environment imaginable, the most like Europa. She is 42 years old. If NASA funds a Europa lander or submersible in the next decade, and if that mission launches in the 2030s, Schmidt would be in her 50s when it arrives. She has structured her entire career around a question she may or may not live to see answered. Kivelson had 97, Schmidt had 42, Pappalardo after 30 years, Culberson out of office. The people who care most about this question have collectively sacrificed the most for it, and the universe, as always, is indifferent to their sacrifice. She has been waiting 25 years for humanity to return to the moon she helped prove was alive. But the ocean has not been waiting. Oceans do not wait. They circulate, they react, they cycle energy through chemistry. Waiting implies something is expected. Waiting implies intent. And the deepest implication of everything in this script is that there is no intent anywhere in the process. Not in the ocean, not in the chemistry, not in the thing the chemistry is building, and not in you. Europa Clipper is currently in cruise phase. It completed a successful Mars gravity assist on March 1st of 2005, passing within 884 kilometers of the Martian surface. During the flyby, the Reason ice-penetrating radar was activated for approximately 40 minutes and successfully produced a subsurface image of Mars, its first real-world test. The spacecraft will swing past Earth in December of 2026 for its final gravity assist, then fall for 3.5 years toward Jupiter. Orbital insertion is scheduled for April of 2030. The first close Europa flyby comes in the spring of 2031. 49 flybys over roughly 4 years, some as close as 25 kilometers above the ice. By 2031, Europa's ocean will have been running for another 5 years beyond today. 5 more years of hydrogen bleeding from the seafloor. 5 more years of oxygen cracked from the ice by Jupiter's radiation. 5 more years of whatever the chemistry does when you leave it alone with energy and time and the fundamental constants of the universe. And when Clipper makes that first pass and Suda opens its gold-coated sensor head and Maspex powers its cryogenic trap and Reason fires 9 megahertz pulses 30 kilometers down through the ice, they will not be discovering Europa. Europa was there before anything on Earth drew breath. What they will be discovering is what the universe does when nobody is watching, what it builds when there is no one to build for, what emerges from salt water and rock and energy and 4 billion years of unbroken darkness. Think about that darkness for a moment, not the poetic kind, the literal kind. Europa's ocean has never seen a photon of sunlight. Not once. Not in 4 billion years. The ice shell above it is tens of kilometers thick. Below it is rock. Between the two is nothing but salt water, dissolved gases, minerals leached from the seafloor, and whatever those ingredients have become after eons of continuous chemical driving. Every process happening in that ocean is happening without light, without a surface, without a sky, without any of the conditions that textbooks told you were necessary for life to begin. And yet the chemistry matches. The energy budget mirrors Earth's. The theoretical frameworks say the physics demands it. The instruments heading there can detect what a single cell leaves behind. Whatever the universe built in that darkness, it was never waiting for us. It was never waiting for our instruments or our theories or our $5 billion spacecraft. It was building before the first cell divided on Earth. It will be building after the last star burns out. The laws that drive it do not expire. The chemistry does not get tired. The energy does not stop flowing as long as Jupiter keeps spinning, and the resonance keeps Europa's mantle warm. The only question is whether you are ready to know what the dark builds when you give it enough time. Whether you are ready to stop being the miracle at the center of the story and start being one more thing the universe built on its way to somewhere else. Because 4 billion years is not how long you wait for an accident. 4 billion years is how long a law of physics takes to finish what it started. And the data arrives in 2031.